Hello, everyone. Welcome back to the class. So, we went over just the start of our Unit 1 Introduction to Physics yesterday. I hope the video was okay and the audio recording was good enough. If it wasn't, please do let me know and I'll try to re record things or send you a script of what I had recorded so that everyone's clear. I'm still trying to learn these different things, so please bear with me. And please do let me know because your feedback is quite important to me. Um, and I can only adapt and change my procedures um, based on the feedback that you provide me with. So we went with our introduction to physics. We briefly went through what is science, what all those steps were, how there are different branches of science, and physics belongs to that one particular as one branch of science. But physics itself is not a single subject, but it is made up of quite a few things, which includes mechanics, thermodynamics, vibrations and wave phenomena, optics, and electromagnetism, which again, they've got their different fields that we went through, and they're available for you in the video that I've uploaded. The presentation will be made available to you. I've forgotten to upload that, but that will be available to you in your course notes on your Google Classroom. So we went through why is physics important. We discussed a few examples, which include a car, kettle, phone, and all those things. And we talked about how each of these processes that happen within the car, they are related to physics and they fit the different branches of physics. Um, we also went through the example of kettle. Again, we fitted all those branches to it, cell phone, all of those things. So moving on, we discussed briefly, very briefly about the scientific method. Once we get to the labs part, we're going to go through this topic in a bit more detail where we'll be defining what the problem is, where we'll be defining or we will form our hypothesis. Um, we will test that hypothesis by gathering the data and analyzing the data and then provide a conclusion. And obviously, we won't be submitting this to a journal or a publication, but your peer review would be something that's done by your classmates here. And essentially, you can match up the measurements because if you're repeating the same experiment, the solution should be the same. So we'll be doing that. And then we'll discuss during the experimentation process and during the labs that we will do um, if we're introducing any bias in the data or not. We talked a bit about measurements, that there is the imperial system and then there is a SI system or System International. We usually call it the SI system because it's brief and we like acronyms. And it's more to do with that it's easily divided into tens, so you can multiply everything or divide everything in by 10. So essentially, you can create bigger or smaller quantities. It all depends how you use them rather than doing, for example, in if you're trying to convert feet to inches, you'll have to multiply by 12, and that's not an easier multiplication. Or if you want to go to a further denomination, it's in 1/16 or 1/12, depends on the instrument you're using to measure. Similarly, if you go into pounds to ounces, that's a different story as well, because if I remember correctly, pounds, 1 kilogram is about 2.205 pounds, and then 16 ounces translates to a pound. So then again, you've got pounds, and then it's further divided into ounces. So you've got 16 divisions within the pound, which is made up of ounces. So it's the multiplication or division. Once you're trying to come up into fractions or anything, it becomes very difficult. And that's why we employ the SI system. Then we looked through this video a bit, and then we went through measuring techniques, which was another video where the person compared the size of the Earth with a grain of sand, and then tried to relate to you how vast the universe was. And that's one way that you can do measurement, or that's called scaling. Then we went through the seven base units, which had the distance, the time, light, mass, current, temperature, and amount of matter that's available within the substance, and what those units are, or what the base units are. And essentially, you can create more units out of these base units. And there's an exercise that should be available to you today or by tomorrow, which you will do, and that should help you with these conversions and then creating new units. We also did a basic conversion of metric to, sorry, imperial to metric units, and then smaller or a higher denomination, those conversions, right? And then there was this other video which was to do with mishaps when people did not use the same units. We will try to do that, and we will do that in our dimensional analysis exercise. Now, today we are going to talk about accuracy versus precision. Now, hopefully, today we'll be able to, if not today, but by tomorrow, we should be able to wrap up this topic. Um, so, the next topic that we were going to talk about today is accuracy versus precision. And as yesterday, what I want you to do is in that little Google form uh, that should be available to you now, we'll have accuracy versus precision. What I want you to do is I want you to write in your own words. Again, it doesn't matter if you're correct, and it doesn't matter if you're wrong. What I want to know is how you want to define it, and what your understanding of accuracy and precision are. So take about a minute and then define what accuracy and precision is. So accuracy refers to how close can you get to the actual value that you're trying to measure, whereas precision is the degree of refinement. So essentially, how close or how precisely you're able to, or how close you're able to get to the actual value, right? So if the value measures, let's say, 1.00001 meters for something, and if I'm using just a regular scale, which has got a maximum or it's divided into millimeter measurements that are visible, what I can measure up to is 0.001 meters, right? Or 1 millimeter. So essentially, that's the highest precision level. So even if the actual measurement is going to be 1.00001, I can either measure up to 1.001 or 0.999. That's going to be my measurement level, and I cannot do anything better than that. And that's going to be my precision.
So when we're talking about accuracy versus precision, right? So accuracy was that whatever you do or what the actual value is, whereas precision is to do with how close you can get to the actual value. So when I'm talking about that, there are so I can measure, so the actual value is 1.0001 meters, whereas I've got a scale which can measure only in millimeters, and the divisions on the scale are millimeters. So what I can do is, and what I can do then is I can only measure up to what is 1 millimeter, right? So that's the one thing I can do. Um, Let me correct this a little bit. So I can only measure up to 1 millimeter. Um, And remember, 1 millimeter is equal to 0.001 meters. So I can technically go as far as 0.001 meter. And what that means is that I can take this scale and start measuring up, and I can get as close to as 1.000 meters, or I can do 1.001 meters, or I can do 0.999 meters. And they're all kind of accurate, right? You may be able to round this off and you'll get to one, and you can round this off and this will lead you to 1 meter as well. But it won't be close to what the accurate value was, right? So this is what you're able to measure given the tools you're using. That is equal to your precision, whereas accuracy is the actual answer that the problem had, or whatever you're trying to measure.
And that brings about this other topic, which is to do with significant figures. Now, significant figures is then the total number of digits, that numeric digits within a measurement that you're certain about plus the one that you're uncertain of. So in this particular example, when I was saying that, well, I can measure up to a millimeter, so that's going to provide me with two digits that I'm absolutely certain about. So my decimeter and my centimeter scale, you can refer back to that table that I'd shown you in yesterday's video. And then the next one is something that I'm uncertain about because I can overlook it. There could be parallax errors. Remember parallax errors. If you don't know that, please let me know. Write that down in the Google form and I'll make sure to include that in our next video. But essentially, that is what significant figures is. So it's the two digits that you're absolutely sure about in your measurement and one that you're not so sure about. So for example, let's say, like I said, if I measure 18.2 centimeter, then this has three significant figures. Two, which I'm really certain about, which in this example is going to be 18 centimeters. And zero point 0.2 is the one that I'm not so sure about, right? I could be introducing bias or errors by just looking at a different angle. That's what parallax error is. Or maybe I'm thinking about something else. So that's something that I'm not sure about, but that limits our case to that this measurement that I've taken is up to three significant figures. Um, so there are multiple techniques that you can use. One thing to do with significant figures, and that's why I don't really like them as much because there are certain rules that are associated with it. And the general rules that you have to follow with significant figures is that the zeros between the non-zero digits are counted as significant, right? So if it was 180.2 centimeters from the previous example, it would be that zero would have been counted. So it would have been four significant figures. The zero is in front of the non-zero digits are not significant. So I can write 180 centimeters and I can do 0.180 centimeters. That first zero is not significant. I can also do zeros at the end of numbers to the right of the decimal point are also significant figures. So you write a decimal point if that measurement's 18.02 centimeters, that zero is a significant figure because it's adding to that value. It means something. And zeros to the left of the decimal point may or may not be. Again, it all depends. If that, because this zero is to the left of the decimal point, if it was in this case, this is significant because it was, remember we talked about 180.2 centimeters. However, if I'm still writing 180.2 centimeters and I write 0180.2 centimeters, that first zero before the one, that is not going to be significant, right? So it all depends. So what I usually prefer to do is rather than going into significant figures and all that debate, I usually talk about decimal points, where you say, well, if you want your answer up to two decimal points, I will say you need to write your answer up to two decimal points. So if your first measurement was 18.2 centimeters, and I say you write it to two decimal points, you'll type down 18.20. So that's your 2 decimal points. So it's a number of digits that you need to write after the decimal point, right? And then there's another technique where you can do the scientific notation. I don't know if you've heard of this before, but essentially in the scientific notation, what you're trying to do is you're trying to round off really big numbers or really small numbers. So it's easier for the reader to comprehend. And that's where the order of magnitude comes in. So 18.2 centimeters can be written as 1.82 times 10 raised to the power of 1. And that 10 raised to the power of 1 is the order of magnitude, and this also relates to the scientific notation. I hope that makes things clear. Again, if it's not clear, please write it down on that Google form, and I will go over this again with some examples. And I believe there are some examples embedded into this video, which will come afterwards.
So when we talk about significant figures, remember, so the rules are stating so the original numerical value in our example that I've stated as 18.2 centimeters, right? So what I'm trying to say here is that zeros between non-zero digits are counted as significant figures. So if this were, for example, if this were a 180.2 centimeters, then this zero that I've written here is part of the significant figure because it's adding value to the actual number, right? I'm going to denote significant figures as SF. Um, and then zeros in front of a non-zero digit are not significant. So I can write this 180.2 centimeter as 018.2 centimeters. Now this zero right here is not a significant figure, right? Because it doesn't really mean anything. Similarly, when we move on to that zeros at the end of a number and to the right of the decimal point are also significant figures. So here what we have is 180.2 centimeters. Now this number right here adds, or this is a significant figure. Why, you may ask? Because it's defining your precision or the precision of the instrument that you're using. So whatever is going to be after or towards the right of this decimal point right here is going to be a significant figure. So it could be 0.20 or it could be 0.20000 or however significant, sorry, decimal points that we can get up to. And similarly, what we can do is zeros to the left of the decimal point may or may not be a significant figure. So for example, if I were to write 180.2 centimeter, now this is a significant figure. However, if my instrument that I'm using is unable to measure this 0.2 value, so I can write 180 centimeter, then this could or could not be. It all depends. So for example, if my instrument that I'm using is only able to do, let's say, measurements of in tens of centimeters. So if this is my ruler, so I can do 10 centimeter, 20 centimeter, and there are no markings in between, um, right? Then I can only do, so I can, so if this, with this scale, if I measure 180 centimeters, what that means is that I cannot really say if this is significant or not because I'm unable to measure this data, right? So it's only significant to two digits because these are the ones that matter. Now, when we talk about decimal points make things quite easy because essentially what we're doing, so if we move back to our 18.2 centimeter value, what that means is that now this value is one decimal point, right? Because there's only one digit after the decimal point. So there's only one digit after the decimal point right here. Now, If I were to do 18.2 centimeters, that makes it that there are two digits, two digits after the decimal, um, and that means there that this is up to two decimal points. And similarly, you can go on in 18.2003 decimal points or 18.2000 centimeters, and that this would be four decimal points. So you essentially you can do measurements or your instruments precise to about four decimal points, and that's why you're including that four decimal or this fourth number, right? And then if you were to talk about significant figures in this case, we've got, let me change the color of the pen. So you, in this case, this is four decimal points, but you've got one, two, three, four, five, and six. Six significant figures. Why do I say six significant figures? Because using the instrument that you're using, you're able to measure one, two, three, four, five quite accurately. These are the digits that you're sure about. This is the one that's been rounded off, and this is the one that you're not so sure about. So maybe, but it still adds to the significant figure part, right? When I say that this is to do with scientific notation, so when I say 18.2 centimeters, this is three significant figures, right? Or one decimal point. I'm going to write dp for decimal point here. Or you can write it as 1.82 centimeters. Sorry, no, hang on. I can write it as 1.82 into 10 raised to the power of 1 centimeters. And this is called scientific notation. Now, scientific notation, as I said earlier, is more to do with large numbers or very small numbers. So, for example, if I was measuring something on the micro scale, so again, let's say if I had something such as 18.2 micrometers, right? Writing this in meters would mean that I would do 0.0000, I believe 0.182 meters, right? So writing this is adding all these zeros is quite useless. So what I can do here is then I can write this as 1.82, and then you count down how many letters that you move. So 1, 2, 3, 4, and 5 into 10 raised to the power of negative 5 meters. And what that essentially means is that you've got you're not wasting time by writing all these zeros, right? And it just makes things really simple. And it's less time consuming. You can also do it for the kilos or tons or mega and all those scales. So, for example, if my computer has 128 gigabytes of memory, what that means is if you go back and refer to that table, giga is to do with 10 raised to the power of 9. So I can write that my computer's got 128 into 10 raised to the power of 9 bytes. But is this value accurate? So 128 into 10 raised to the power of 9 bytes. Well, what I would say is that this is not right. Why? Because essentially, what with scientific notation, what you have to do is you have to have one digit, then a decimal point, then some round numbers given to the accuracy that you're trying to measure. So it could be 2, 3, 4 decimal points, and then into 10 raised to power whatever that value is. So if I was to say that 128 bytes, 128 gigabytes essentially, and that G is standing for 10 raised to the power of 9, and then I've got these in hundreds, what that would reduce to is 1.28 into 10 raised to the power of 2, right, into 10 raised to the power of 9. Now, mathematically, what you can do is 1.28 into 10 raised to the power of 2 into 10 raised to the power of 9. When you've got same numbers, you just need to add these two. So what you can write this as is 1.28 into 10, 2 plus 9, and you've got 1.28 into 10 raised to the power of 11 bytes. And that should be an accurate answer in scientific notation.
So the next part that we were going to talk about was dimensional analysis. What I had actually planned for you was that you would be doing this on your own. So there would be a timer, and you would go onto the internet and try to find what these different quantities are. So area, volume, weight, density, speed, energy, acceleration, and what those units are. So if I am to go back a few slides, we remember we talked about these base units. So essentially you could use these units right here, and then you can, using these units, you can essentially create um, new units and new units of measurement. So you can measure um, new data points or new types of things using those 7 base units. And all these quantities that you see here on this slide are essentially based from there. So what will happen now is the screen will cut off, and I'll move on to the Google Jamboard screen capture thing, and we will work through these quantities together.
So when I'm talking about dimensional analysis, what I mean is that you can start creating your new units by using the 7 base units that we're talking about. So for instance, let's take this, oops. So let's take this square here. We've got one side which measures a centimeters, and then we've got the width which measures, let's say, b centimeters, right? So we've got 2 dimensions. What I can do then is, if I were to calculate the area right here, what the area is, let me shade this region. What you can do then is that area is given as the length, which is measured in centimeters, times b centimeters, right? So this is going to be a b centimeter squared, right? Same um, bottom, um, same bottom figures could be, then the powers could be added when you're multiplying them, right? So that's a mathematical rule. So area is going to be AB centimeters squared. When we, let's say, for instance, start talking about volume, so let's say we've got a let's say we've got a cuboid here. So let me create a rectangle here. Lines draw towards the bottom, and so we've got length is measured again as a centimeters. Then we've got the width, which is measured in b centimeters, right? And then we've got the height, which is now measured in c centimeters. Oh boy, poor choice of units. But anyways, what I was saying is, so you've got ABC, or a cuboid which measures a centimeters by b centimeters by c centimeters. The volume then is going to be, well, you just multiply everything together. So it's going to be a centimeters times b centimeters times c centimeters, right? And I'm just underlining the dimensions away from the units so it's easier for you. So this is going to be then A, B, C centimeters. And then because there's 1, 2, and 3, this is going to be centimeter cubed. And that's your volume. So what you've now done is you've used your base units of centimeters here. So actually it's meters, but then we're converted it down to centimeters because it's easier to visualize and it's easier to. So anyways, it's measured into ABC centimeter cube, and we've created now 2 different units. So we've used the base unit of length, which was centimeters in this case, or converted to centimeters to create area, which has the base units of centimeter square, and volume, which has the units of centimeter cube, like in this example that we just did. So let's talk about density next. What I mean by density, or what do I mean by density? Now, density is how dense an object is. So going back to our cuboid example, let's say, so I've got again, this cuboid, we've got one. Again, the measurements are still the same. So we've got sorry, this was B centimeters. Let me erase this and let me do this properly. So we've got A centimeters, we've got B centimeters, and then the height was C centimeters, right? Now I've got two cuboids which are of same type, so I can do this again. I'm pretty bad at drawing. I shouldn't be. I'm an engineer, but I'm pretty bad at drawing. So A centimeters, B centimeters, and this Chromebook doesn't really help much. There are latency issues, but anyways, so we've got A, B, C centimeters. So now what I can say is that this one is made out of wood, and this one is made out of steel. Now, if I were to ask you which one is going to be the heavier one, the natural answer is that you're going to say steel. Why is that? Because, well, steel is much more dense. Going back to our volume part, what we know is that volume is, for both of these, is going to be ABC centimeter cube, no matter which object you're looking at, because the dimensions are the same and it's a cuboid shape or a block shape. Steel is going to be more denser. And why? Because steel has a higher molar mass compared to the wood, and that means that wood is essentially lighter. So if you were to put this on scale, the mass of wood is going to be less than the mass of steel. So when it comes to density measurement, I'll have to, let's say, erase this density part right here because I'm running out of space. What that would mean is now density is simply measured as mass over volume. So if I were to now measure this, let's say these blocks are small enough and they're measured in grams, what I would get is, if mass is in grams and then volume is in centimeter cube, what I would get, the density units is, are going to be in grams per centimeter cube, right? So that's one way to do it. Next, we can talk about speed. When we talk about speed, we all know what speed is. Not the movie. We're not talking about the movie here, but let's say we've got a car here or a truck, whatever you want to do it, right? So let's say it's some sort of a truck. Right? It's covered. It started at point A. Now it moved to point B. It took the truck about 1 hour and 30 minutes to cover a distance of, let's say, 100 miles. Now, what would the speed be? It's basically distance over time. Um, Let me write speed here, is equal to distance over time equals to speed. So if I were to add the units to this part, so it's 100 miles divided by 1.5 hours. And whatever that calculation ends up to be, you're going to get miles per hour. Right? Now, this is not in SI units, this is imperial units. If you were to convert this into SI units, are because there are no different units for what do you call it, for R, no different units in imperial or metric system for R's or measurement. You can convert miles to metric system, and that's just given as imperial to metric for miles is given by a simple factor of 1.6. So you just multiply your answer by 1.6, and that would be converted into miles. Miles per hour would be converted to kilometers per hour, right? And that's one way to do it. You could also, going further, you can also convert kilometers per hour to meters per second. And essentially, what you do then is over here, because it's a kilo is equal to 10 raised to the power of 3, which is equal to 1,000 meters, right, in kilometers. And then R is going to have 60 minutes into, and then each minute has got about 60 seconds, um, right? So you what you end up with is 1,000 meters by 3,600 seconds, and then you can cross these out, and it's going to be 10 by 36 is the conversion if you want to convert kilometers per hour to meters per second, right? So whatever that conversion is, you just multiply it with that, and you'll get your answer in meters per second. Acceleration. Um, well, let me pause here, and I'll give you about, let's say, 5 minutes. And what you can do is then you can use Google search engine to find what acceleration is, and then what the units for energy are, and what the units for weight, or what the unit for weight is, right? And then you've got about, let's say, 5 minutes. What I would prefer you to do is that you go through and you do the step by step calculation like I did. So look for the formula that applies to each of these, and then do the conversion from, so meter divided by seconds, and that should give you meter per second for speed, right? That sort of thing. And we'll continue this after 5 minutes.
I hope that made sense. Uh, and what is going to happen next, and what we're going to move on to, are some visualization techniques. Now, what you see here is scatter and line plot combo. But before I start talking about all of this data, um, yeah, the screen's going to cut off again, and we'll move on to the Google Jamboard presentation part. And what you'll see here is how you're using all that data to measure, or you using different sorts of data, or had different data, and how you can use the visualization techniques to present that data in a visual format on a graph paper or whatnot.
So the very first slide that you saw on the visualization techniques was a scatter and a line chart. Now these are very important tools in not only presenting the data but extracting some certain relationships from that data or whatnot. So what I can do now is, for instance, let's talk about, let's say that you go on a journey on your car, and you take multiple journeys. So let's say we've got a number of journeys around here, then we've got the time taken to do that journey, and then we've got the distance. So we're not taking any other factors here, but let's just say that we've got this. So we've got distance, we've got time. Let's say you did 5 journeys, so 1, 2, 3, 4, 5. For the first journey, which was about 100 miles, you did, or sorry, let's say 100 kilometers. It took you about 60 minutes, right? Or 1 hour to conduct that journey. The second one was a small one, 10 kilometers. It took you about 10 minutes to do so. The next one was 50 kilometers. So let's do this. So 50 kilometers. So let's say I can write kilometers here. I can do minutes in here. So I don't have to write minutes again. And that one took you about, let's say, 50 minutes. This next one is going to be, um, it took you 20 minutes to cover 40 kilometers. And then this one was where you were going really fast. It took you about 45 minutes to cover another 100 kilometers. Right. So how are you going to present the data? Now, if I were to do a simple line chart, so now here you go, your distance is right here, time is independent because it doesn't really matter. Time is always going to move forward. So you've got distance, always write your units. You've got your time, which is in minutes. Now I can do, let's say, in denominations of about, so 20, so 20, 40, and then 60, right? And the maximum that we traveled was about 100 kilometers. So let's get 100 kilometers, and halfway through is 50 kilometers. So we can do 25 here, and then we can do 75 here, right? So if I were to just add these, add this data point in terms of just points, so I can do the first one took me 60 minutes to cover 100 points, so that's one dot here. The second took me 10 minutes, around somewhere around here, to cover 10 kilometers, so that's going to be somewhere around here. The third one took me 50 minutes, so somewhere around here, to do 50 miles, sorry, 50 kilometers. So that one's going to be here. 20 minutes for a 40-kilometer journey, so there's 20 minutes, and then 40 is going to be around here somewhere, and 45 minutes somewhere around here for another 100 kilometers. Now that's one way you can visualize the data, right? So that's a scatter plot. If I were to do a line plot, however, I'm just going to connect the dots again, but essentially what would happen is I would start with the first data point, because the data isn't sorted, right? So when you're presenting this, or when you're trying this in uh, Microsoft Excel or Google Sheets or Macintosh Numbers, what they will do is they will essentially just start plotting from the first point right here and then move downwards without and they won't care about the ascending or the descending order. So what would happen here is if I were going to do a line plot, so the first one is right here, the second one is 10 minutes, so it will draw a line down here. Then the next one was 50 for 50, so it would do this thing. The next one is 20 for 40, so it would go like this and this. Now this one does not clearly make any sense, right? So charts, it's up to you. It depends how the data that you obtained, how that looks. But essentially line charts would be better if this entire data was in an ascending order, and then the distance, which was dependent on the time, is going to be was sorted accordingly. However, a scatter plot in this case is a better one, is a better choice, because what this allows you to do is essentially give you the chance to see how everything would relate. So let me change the color here. So I'm going red. But what this means is that red, I can do a best fit for this curve. So if I were to draw a line between these points right here, so which is equally distant from all these points. So let's say I would do something like this. What that would tell me is how my distance traveled is related to the time. So I can do an average estimate of how long it would take me to cover a certain distance. So I can then essentially do a gradient plot. So I can take this, note down this point right here, right, and then I can do the same around here. So I can do this, and that should give me a slope. But this is one way to visualize data, which allows me to extract data out of it. And scatter plot is a very powerful tool in that regards, right? And we will do more about how you can extract information out of this data on a later date, but that's one way to do it. So one other method to visualize data are bar charts, and bar charts essentially um, allow you to compare uh, the results that you may obtain for any given measurement. So, for instance, let's start with a bar chart plot. And for instance, let's say I'm teaching a physics class. So I've got, let's say in that physics class, I've got about 6 students, one, two, three, four, five, and six. And then I give the students in this class a test with a maximum points score of 10, and just randomly jotting down some numbers. So I've got 5, 4, and then somebody scored a 2, another one scored a 10, someone scored an 8, and the other one scored a 9. So just random figure set here. So what I can do then is I can do a line plot or a bar chart plot. So I've got my y-axis and x-axis, and always remember to label your axis. So I've got students here. So let's say I've got 1, and then 2, and then 3, and then 4, and then 5, and then about 6 here, right? And then let's say I've got 1, 2, 3, 4. With every separation of 2 blocks, it goes up to 6, 7, 8, 9, and 10. And this is y-axis, and this is points. What I'm going to do now is I'm going to do a bar chart of all these points that you see right here for against the number of students that are plotted on the x-axis. So student 1 scored 5 points. I'm going to go here, and I'm just going to draw a bar around here. So that's what student 1 scored. Student 2 scored 4, so I can do this. That's student 2. Then I've got student 3, which scored about 2 points. And then that's one chart. Student 4, on the other hand, scored 10 points. So I can take it all the way up here, do this, and drop it back down. Sorry for the poor lines. Student 5 scored about 8 points. So I can do this. And then student 6 did 9 points. So another one up top here. And that's a bar chart. So what this shows me then is how the different students performed in their class test, right? So that's one way to represent the data. I hope that's clear enough. So it's just bar charts, a way to compare the data without trying to extract any information from it. Now you can do combo plots, but we'll talk about those at a later time. And one of the last techniques that we're going to talk about today is, or visualization techniques that we're going to talk about, is pie chart. Now, pie chart is another important visualization technique which allows you to see how the data has divided, or how the data, some sort of information that you had, um, was used up, or how it was divided into different percentages that completed the entire picture. So a pie chart usually looks, well, as the name suggests, a pie, right? So it's a circular, and the whole pie would denote that it's 100%. Now, for instance, if I were to say, let's say, again, let's take the example of a class. I've got my physics class. I've got 5 students in this case. I've got one, two, three, four, 5 students, and one day I decided to bring in some candy, right? So I've got a candy which is, let's say, a 30 pack. Um, and I left the packet on the student table, on the teacher table, so the students can come in while they're working and they can start picking out as many pieces. So student one took about 5 pieces of candy. Student two took 6 pieces. That's 11 pieces. So we've got 19. Student three decided to take only 3 pieces during the entire work. Four did eat another 7 pieces. So that's what, 10 and 11, 21. Student five, someone like me who got a bit greedy and took 9 candies out of the pack. So that's summed up to 30 points, or 30 candies. So what this would basically mean then is that student one got 5 out of 30, so that's about 20%. Student two got 6 out of 30, so that's going to be, sorry, this is less than 20%. This is 20%. This is going to be around 18%, but whatever that percentage is, this is going to be 3 out of 30, so that's 10%. Um, so on, and this 9 is going to be 30%, and 7 is going to be just a bit over 20%. So just a bit over 21% right here, right? So let's just say 22% to make everything whole around here, right? So that's 100%, I believe. So 30, 30 and 60, and yeah, 40. So if I were to plot this, then let me clear the frame here. If I were to plot this, what would happen is, again, this is pie chart that we're dealing with. So we had student one, two, three, four, 5. We had 18% share. We have 20%. We had 10%, I believe, 22%, and 30%, if I remember correctly, right? Percentage share, I can write this from the candy and the number of students. So what I can do then is, if I were to go back to my pie chart, um, which is represented by a circle here, I can do then is that student one had, um, so I start with this, and let's start clockwise. Student one took 18%. Student two took 20%, which is going to be slightly bigger than that. Student three took just 10%, which is just about this. Student four took 22%, which is around here, and this is 30%. So now this is not, again, this is not this is not to scale here, but what this means is that we've got 22%, we've got 10%. Again, the Excel would provide you with this data set, or this percentages, where you can label it, but this is one way to represent the data. And I've got a few other examples that, once we move on to the presentation back again, it should help you. One thing I would like to add here, though, is if these problems weren't clear, please let me know in that Google form that I've shared, so I can go back over these the next time we meet. Thank you.
So one way to do, or one way to go forward is, I got some data, and like I said before, that because you don't know what value you're going to get, it could be any random value. So one thing you could do is you could do a scatter plot. Now this is some data that I got from a mathematical model that I've been working on, and it measures, tries to measure the atomization rate of water in kilograms per second. So it's about 500 kilograms a second or whatnot. And this is from the simulated atomization rate. This is from a mathematical model that I've been trying to work on. So these are from the experimental results, and this is from the simulated data. Um, so as I'm going through my data points, or as I'm going through the different test conditions for my model, what is happening is I'm not getting a straight line. So if I were to get, so when I input, let's say 500 and I get a 500 output, I would get a data point here. I would get another for 1,000. If I input 1,000 for 1,000 case, I would get an atomization rate of 1,000 kilograms per second. It would plot here and so on and so forth. What in that case, what would happen is I'll get these data points on this line, and I could just use just a line plot to draw the plot. In real life, though, what is happening is for certain number of conditions, when I input those conditions in, I will get, so for example, or for instance here, right here, this is about 350 kilograms per second. What I'm measuring is about 450 kilograms per second. But my next data set is not supposed to be for 500. It might be something around here or something around here, so it could move. If I were to do a line plot, what your Excel's Google Slides or Google Sheets would do is it would do a line plot through those points. So as the points would appear, the better thing to do then is to use scatter plot. And when you're using scatter plot, it essentially is doing it's running through and it's just plotting these points, and there's no line joining them together, so it just looks better. And then what you can do then is you can do this trend line sort of thing through it, which is going to predict what the relation between these two, between the independent axis and the dependent axis is. um, and we'll talk about these a bit more later on. The other part that we've done was to do with bar charts. Now, bar charts are essentially something, um, or to do a comparison with. So right here, again, this is to do with the accuracy of the data that I'd shown you earlier. So was the results that I've seen, some are within 1%. So what it's showing you that there are certain, so there's about 2% of the results are within 1% or are accurate to 1%, and there's about 5%, around 16% of the results are around 16% accurate, or are, sorry, within 10% accuracy, and so on and so forth. And some, nearly almost all the results are within 50% accuracy, right? So these are different combinations I did, but essentially a bar chart would give you a good comparison. Now, this is another example of from my uh, personal finances. I like to create an Excel file or a Google numbers, sorry, numbers is from pages, Google Sheets, I'd say. Um, and I like to create a pie chart. As we discussed before, pie charts are usually to show you the percentage occupancy by different categories that you're using. So I like to do my expenses at the end of the month, and what I've divided everything into is, so I've got my household expenses, which is my rent. It has to do with my bills and my Netflix, Amazon, and whatnot. Then I've got another section, or blue, as you can see right here, for my car, so car expenses, insurance, fuel, whatnot. Then I've got something to do with outside dining. We're not doing so much so because of this current COVID thing. And you've got grocery, a good chunk of budget goes to the grocery. Then extras are something that I need, or that need, but they're not part of the grocery or anything else. And then there's this unnecessary expense section. So what we're wasting money on and whatnot, or what we could do without. So that's something extra that I've added. So this is how you can do, and a pie chart is very good example of where you've got multiple categories and they're summing up to 100%, and you can show how much share that each category is to the total percentage. And it's good for a number. good for expenses, it's good for budgeting, it's good for all those things. Or if you're basically working towards 100 percentage and you wanted to show how that 100% is divided into different categories, you can use a pie chart to do so. And I believe that is the end. No, that's not the end. Sorry, I've got some work for you to do. Um, and what I would like you to do now is I want you to open up your Google Docs, and you'll also need your Google Sheets. And what I want you to do is I want you to go through these three different examples that you're able to see here. Again, the PowerPoint is available for you on your Google Classroom. You can open that up. You can have this slide open so you can go back and forth. What I want you to do is, for example, one, um, look at the journey to your school, think in terms of distance, speed, or time. Um, and what I want you to do is I want you to plot it. So, for example, you're starting from home, you're reaching school, you covered 10 miles. Um, you will plot that against time. You could also do is you could do distance or speed versus time, how fast you're traveling during that time. So if it takes you 15 minutes to reach the school, there will be times when you're moving, there will be times when you're not moving. Um, so I want you to present that as part of your in a visual manner. Um, Example two would be to go through the CDC website. There is a lot of coronavirus information that's going on, so you can compile that data by state-wise, and then how would you present this data, right? Do that. Now you can do the recovered versus the unrecovered figures per state, present that data, and finally, in example three, what you have to do is you have to do US versus the world. So represent the cases per country as a percentage, right? So you kind of know what I'm trying to get to in this last example. So you go through, you compile all this data set, um, and you present that. And once you're done with it, so you have the remainder of this class. I'm not sure how good we are on time right now, but we would be around, I think you'll have around 30 minutes or so. You'll have 30 minutes of working time tomorrow as well once you return to class, and then you can essentially complete this assignment. And once you've completed it, since this is an in-class activity, please submit it to me when you're done, and then I'll have another set of lecture planned for you once we return. Yeah, again, if you have any questions, please use that Google form and submit it to me so I can adapt and change my recordings according to your needs. And please do let me know and tell me what's working, what is not working, if the audio is correct, if the explanations are okay, or if they're ample or not. If you want me to repeat those, if you want me to go through a few more examples, please do let me know, and I'll see what I can do, and I'll try to incorporate it into the new recordings that I'm making pretty much every day. At least I plan to do those. If I cannot do it the next day, I will try to add those to it the very next day. Thank you very much.